When we start looking at the exchange of gases between the lungs and the blood and the tissues, we have to look at both internal and external respiration. Now, I've mentioned those two before. External respiration is the air coming into your lungs and then from the alveoli going into the capillaries, or capillaries back to alveoli. Internal respiration is when it's going from the blood into the tissues or tissues back to blood. Now, to understand that, we have to look at the physical properties of gases and the composition of alveolar gas. Because together, that's going to help us dictate the pressures and the movement and the properties of all these different involved parts. So, let's take a look. We start with Dalton's law. Now, there's a lot of writing up here, but the basic idea is when you start looking at Dalton's law, it's talking about the mixture of gases. The pressure of each individual gas, if you add each individual pressure together, equals the sum of the whole mixture. So the sum of all the pressures exerted is that what you're looking at. So when you're thinking about the air we're breathing, for example, there's nitrogen, there's oxygen, there's carbon dioxide, there's water vapor. All those gases, nitrogen, oxygen, carbon dioxide, they have what's referred to as partial pressures. And together, that makes up the overall pressure of this gas we call air. Now we know that at sea level, the pressure is 760 millimeters of mercury. That means that 760 millimeters of mercury is made up of partial pressures of nitrogen, of oxygen, of carbon dioxide, of water vapor, H2O. They all add together to equal that 760 millimeters of mercury. So if you look at this one, this breakdown, you'll notice nitrogen, 78.6% of the gas mixture. Now the rest are all smaller. Looking at oxygen, just about 21, water is 0.4, carbon dioxide 0.04, then the others 0.06 if you're adding them all up. But look at the partial pressures. The partial pressure of carbon dioxide, 0.04 is the total percent of composition. The partial pressure then is 0.3. If you look at the nitrogen, 78.6 is the percentage. 597.4 is the partial pressure. Basically, if you're trying to figure out how that works, 760 millimeters of mercury is the overall pressure at sea level. We know 78.6% of that is nitrogen. So if you take 560, multiply it by the percentage, 78.6% or 0.786, that gives you 597.4. So each one of the partial pressures is going to be its percentage composition times the actual pressure overall. At sea level, 760 millimeters of mercury. So look at how everything's mixing together to make that full composition. Then we have what's called Henry's law. Now in Henry's law, we're looking at how liquids are dissolving. So liquids are going to dissolve based on their pressures. So you're looking at how each gas comes in contact with liquid and then how it dissolves across. Why do we care? Well, you know that air you're breathing in? You need that oxygen, which is a gas, to dissolve into your blood, the liquid. You need the carbon dioxide to dissolve out of that liquid. So that's where Henry's law comes into play, looking at how these different gases are dissolving. Now, at equilibrium, they should be equal. The partial pressure in the two phases, air and liquid, should be equal. But we're not staying at equilibrium. We're not staying exactly the same. Our blood's flowing, our blood's moving. So the blood that was in your lungs a few seconds ago is not there anymore. It's already moved out. Different bloods come in with a different composition of gases. So the amount of gas that dissolves is really depending on its solubility as well as some of that pressure. So what's interesting is carbon dioxide, 20 times more soluble than oxygen. Now if you're thinking, hold on, oxygen's kind of important. True. which means our pressures have to compensate for this solubility difference. And I'll look at that in 1 second, so don't forget that one. Carbon dioxide, 20 times more soluble. Other one at the bottom, very little nitrogen dissolves. It doesn't mean you have zero nitrogen in your blood. You do have some, but very little is dissolving. Just based on its solubility, it's not really going to dissolve. So here's our alveolar air. So this is what's inside our lungs. You'll notice we still have a high percentage of nitrogen. That makes the highest partial pressure. Then look below that. Look at the oxygen, water, and carbon dioxide. Those are all different than your atmospheric, which means the partial pressures are also different. Take oxygen, for example. In the atmospheric, that was almost 21%. Here, it's only 13.7, which means its partial pressure is lower in the lungs than the air around. Why is that? Well, inside your alveoli, where's the oxygen going? The oxygen is going into the capillaries, which means it's being pulled out of the gaseous state in the alveoli and into your blood. Therefore, the percentage becomes lower. But notice these two, partial pressure of water and carbon dioxide. Both are much higher, which gives a much higher partial pressure than what atmospheric is. So that means, why are those happening? Let's start with the carbon dioxide. That carbon dioxide is much higher for the alveolar partial pressure compared to atmospheric. So there's more carbon dioxide there. Why? Because as your blood comes into your lungs and alveoli, it's dumping or dropping off carbon dioxide. You're increasing the levels of carbon dioxide in your alveoli. How about the water, H2O? Why is that higher? Remember, as you inhale through your nose, you're warming the air and you're adding moisture to the air. That means that increased moisture in the air equates to a higher water vapor, a higher partial pressure of water. So the composition of the alveolar gas, what's inside your lungs, is going to be slightly modified compared to what's around us because of how the gases are being used, because of what we're absorbing, what we're giving off, and what we're adding into the air when we breathe. All right, so external respiration, exchange of oxygen and carbon dioxide across the respiratory membrane. Now the goal here is to have the oxygen going into the blood, carbon dioxide coming out. That's what will be happening as long as everything's in proper balance. So you're influenced by those partial pressure gradients and gas solubility, which we'll look at that a little more in detail. But then you also have this ventilation-perfusion coupling. Ventilation, the breathing in and out. Perfusion, the movement across the membrane. Your body's going to make sure that the air coming in is going to the appropriate spots, the appropriate alveoli. It doesn't simply go to every one of them equally. Your body controls where, this air needs to go to this alveoli, that alveoli, because they have higher amounts of carbon dioxide, lower amounts of oxygen. But this one over here has low carbon dioxide, high oxygen. Well, you don't need more oxygen going there because you already have oxygen. So your body's going to be using receptors to monitor the different levels inside the alveoli and help to make sure the perfusion, where things are going with the ventilation, is coupled. So it's efficient and it's working. And then, of course, these structural characteristics. If something is smaller, there's less airflow going through it. Larger, more airflow going through it. If you have different surface tensions causing blockages or increasing turbulence, all of these can change how things are flowing for the external respiration. So we're looking here now at the partial pressure of oxygen. Notice that in the venous blood, partial pressure of oxygen is 40 millimeters of mercury. So that's the venous blood coming back to the lungs. But now the alveolar partial pressure, this is what's inside the alveoli, is 104 millimeters of mercury of pressure. That 104 millimeters of mercury of pressure is a whole lot higher than 40, which means you've created a gradient. The oxygen is in a higher concentration inside the alveoli and in a lower concentration in the venous blood around it. The oxygen wants to go into the blood. Now, as far as this goes, if you look at reaching the equilibrium of 104 millimeters of mercury, takes only about 0.25 seconds. That's about a third of the time the red blood cell is actually in your pulmonary circulation. Because the air that's in your lungs, you keep breathing. So you keep that 104 millimeters of mercury pressure. That's going to go into the actual alveolar blood as it's going from 40 up to 104. That's the goal. Now, when you're working out very heavily, you're really breathing deeply, you might not have enough time to get there because your blood flow is increased. But at rest, you should be able to reach pretty close to that equilibrium by the time the blood leaves the lungs, the pulmonary circulation. All right, carbon dioxide time. We're looking at the partial pressures, again, inside the venous blood and inside the alveoli. Venous blood, partial pressure of carbon dioxide is 45 millimeters of mercury. Well, that's not that much different than the oxygen. Oxygen was 40 millimeters of mercury. But look at now. The alveolar partial pressure is only 40. That means inside the alveoli, that partial pressure of carbon dioxide is 40 millimeters of mercury. So now we've only set up a gradient of 5 millimeters of mercury because you're going from the blood, 45 millimeters of mercury, into the alveoli, 40 millimeters of mercury. But remember, oxygen and carbon dioxide are flowing at roughly the same rate. So if we have a 5 millimeter of mercury gradient here, but we had, what was that, 64 millimeter mercury gradient for the oxygen, they're flowing the same? That's because carbon dioxide is 20 times more soluble. So that increased solubility is helping the lower gradient be equivalent to the larger gradient of oxygen. So that 20 times solubility is what makes up the difference. Overall though, because of the higher carbon dioxide solubility paired with the lower gradient, and then the lower oxygen solubility paired with the higher gradient, are both diffusing and exchanging at about the same rate. So a little about partial pressures, especially with carbon dioxide and oxygen, alveolar and venous blood, and how everything's working together to make sure you're staying in equilibrium.